Raj Desai. I'm the Executive Director at TIE Silicon Valley. And on behalf of TIE, really delighted, and Qualcomm, our supporting sponsor, I'm delighted to welcome you all here this evening. This is a full house. It's terrific to see you all here. It's a very interesting topic. And we at TIE are very appreciative of our affiliation with Qualcomm. Ever since early part of this year, we partnered both through TICON as well as throughout the year to engage many of our early stage entrepreneurs with what Qualcomm does here in terms of innovation, in terms of what's changing in the marketplace as it relates to their business. How many of you are TIE members? How many of you coming to a kind of TIE associated event for the first time? Okay, welcome. Hope to see you more often. We do events regularly on various topics. Membership at TIE is very nominal. At $150 a year, you get about 40 or 50 dinner events, including a glass of wine at no charge. So you attend 10 of these events and it's kind of paid for. Also our annual conference in May every year at the Santa Clara Convention Center. It's a great event, 4,000 plus people, 200 speakers, Friday, Saturday program, 100 plus companies showcasing in the expo floor, about 40 countries participating, and members get a significant discount, less than the cost of food and beverage. So do look out. It's May 16th, 17th for next year, and we will be announcing our keynotes and the structure of that program by Christmas. TIE, founded about 21 years ago, the concept was very much to help entrepreneurs and foster entrepreneurship. There was no vision at that time to be a global organization, but as we started receiving lots of international visitors and seeing what we were doing at TIE, they basically pulled us into various regions and said, can we do the same in London? Can we do the same in Dubai? Can we do the same in cities in India? So we're now in 60 cities, 18 countries, including Tokyo, Hong Kong, Sydney, Australia. Just launched Lisbon, Portugal, and we're looking currently at Mexico, Brazil, Trinidad and Tobago, and so on. Again, we're not seeking and reaching out to form chapters. It is people, entrepreneurs like yourselves, out in those regions coming and approaching TIE to do a similar program for their community, and we're very happy to help. Currently, we're very aggressively helping folks in Palestine. We believe that entrepreneurship can also exist there despite all of the troubles that you hear about, and we at TIE are very, very supportive of those initiatives. Charter members, number of charter members here, I see. Zain here, Naresh Batra, if I've missed a few, raise your hands, charter members at TIE. Rajiv Patel, yes, very good. So charter membership is the core of TIE. They are the very highly accomplished entrepreneurs with a lot of experience and the passion to give back. That is the founding of TIE. Charter members have the passion to give back through mentoring, advice, guidance. So anyone can apply at TIE to be mentored on any particular business entrepreneurship endeavor that they wish to pursue. And at no charge, we basically offer that mentoring service. So reach out to TIE and engage our charter members to help you in your entrepreneurial journey. With that, I'd like to proceed and not take up time from the very interesting panel and topic that we have for this evening. I'd like to introduce Jim McGregor. Jim is a principal at Tyras Research, has over 25 years experience in semiconductor and embedded systems, and advises many industries. With that, I think he's going to also introduce us to our host for the evening. Jim, please. Let's welcome Jim to the podium.
Thank you. Okay, thank you for joining us here at Qualcomm. It's my pleasure to introduce Raj Talluri. He is the Senior Vice President of Product Management at Qualcomm Technologies. If you don't know Raj, he's been around the industry for quite a while and very well respected. Not only is he in charge of the Snapdragon and application processors at Qualcomm, but he was really involved in the design and development of the first application processors with Texas Instruments and has an extensive experience through Texas Instruments. So please give me a hand in helping Raj.
Okay, thank you. I think we're going to start with a short video and then.
Listening to you, I only listen to my heart. No, you can't bring us down. We're too strong, we got muscle, we are tough.
All right. Well, good evening. Thank you all for coming. And that I promise will be as much marketing as I do today. So my name is Raj Talluri. I'm based in San Diego, and I work for Qualcomm. And I've been there about 4 or 5 years. Before that, I was at Texas Instruments for a long time, maybe 15, 16 years. I've been building application processors and processors that do different kind of consumer things in phones, TVs, tablets, and so on for pretty much my whole career. So it's really my pleasure to talk to you about a concept, our way of computing that's getting more and more popular in an application process now. And it's something that we are doing at Qualcomm, and I think the industry is slowly moving towards that. And I'll introduce that to you today and talk about some of the challenges and some of the opportunities. And I'm also going to try and show you a couple of demonstrations of heterogeneous computing in action so that you get a feel and an appreciation for that. So, we'll keep it informal, and I'll go through, I think I have like 45 minutes, and I'm just looking around the audience here. I think I shouldn't have too much problem speaking fast, because usually I try to slow myself down. I'm not really good at it, but I think this audience can probably keep up. All right, so let's talk about application process. So first thing is, how many of you guys here know about Snapdragon? Anybody heard about it? Okay, this is going to be easy. So we make processors that go into smartphones at Qualcomm, and we make processors, we make connectivity, we make modems, and so on. We've been fortunate. We've had good success in the marketplace. Today, I think most of the high-tier phones, if you buy in the market, particularly this year, whether it is the Samsung Galaxy Note 3, the LG G2, the Sony Xperia, or the new Nexus devices, pretty much all of them use Snapdragon 800, which is our highest performance processor. And when we do those processors, our goal has been really to do great consumer experiences. And mobile devices have really become devices that you use for essentially consumer electronic things. I mean, you like to watch videos, you like to play movies, you like to take pictures. You like to do some productivity stuff, but really they've become your all-in-one entertainment device and your productivity device in one. And that has led to some interesting challenges in designing processors that go into that. So the first thing is, just give you a, kind of an appreciation for the size of the market. And if you look at the size of the market today, it's, really the industry is shifting towards, I'm just going to show you some numbers here, 7 billion cumulative shipments of smartphones, 4 times that of PCs. So it's really a phenomenal number to just get your head around, the size of the market, the size of the opportunity. And we believe that in a couple of years, you probably won't have any other phones except smartphones. And that's actually something very, mind-boggling to think about. When I started working on smartphones, there is a lot of discussion on whether, whether 1% of the market, 2% of the market, 5% of the market, or people want smartphones and so on. Today, actually, you don't even think about it. That's the only kind of phone people seem to buy. It's kind of an antiquity if people use a phone that they flip or it's not smart. So it's pretty amazing to watch that happen. And what that has done is it has become the largest platform in the industry. By what I mean by that is a lot of the innovation, whether it's software, whether it's applications, whether it's process, whether it's silicon design, whether it's cameras, it is happening in the mobile platform, just by the sheer magnitude of the platform in terms of scale. And it brings some unique challenges. I mean, just this number, 160 billion app downloads in 2017. I mean, it's just a number that's really hard to even comprehend. But that's the opportunity and the challenge in front of us. And something I tell people just to develop an appreciation for this. When you buy a smartphone, when you get a smartphone and you start using it, initially there's a lot of software in the smartphone that either comes from Qualcomm or comes from the OEM, Samsung, LG, so on, or the operator. Now you give this phone to somebody, depending upon how adept they are at using it, in a few short months, or a few short days, or a few short hours, depends on who you give to, there'll be more software in that phone that's neither from Qualcomm nor from the OEM or the operator. There'll be more apps running on that thing than from anywhere else. And that is actually, if you think about that, think about the challenge of someone who designs an application processor when you don't know what's going to run on it, right? That's the challenge that we are talking about. So because you don't know what applications will run on it, you don't know how many of them will be there, but you're designing that. And the other challenge is, I'll give you a feel for timelines here. Typically, it's been getting harder and harder and longer to design apps processors. So, for example, right now at Qualcomm, when we design a high-end apps processor, it typically takes us, I would say, 6 months to define a spec, just to collect market requirements and so on. And then probably take us another year to execute the design, tape out the part. And by the time we get samples, it takes another 3 months to get samples now in deep Qualcomm Technologies. And then it'll take us another 8 to 9 months to get all the software ready on it. And we get it to our customers. They typically take between 6 months to a year to write all the software on it. So by the time you get a phone into the hands of the consumer, it's between 3 and 3.5 years. So anything we are working on today is what's going to be in the market in 17 and 16. So that's what the lead times we're talking about. So we are trying to solve problems and trying to solve, anticipate the requirements that far out, and that's a tough problem. And so many times people ask me, how do you guys do this, and how do you anticipate what's going to be there? And I have my secret, which is I have this black round crystal ball which I keep in my office, and I pull it out and there it is, right? It's worked for me, but I don't tell you where I keep it, but it worked for me. But Joseph, it's a tough problem. It's a tough problem that faces the industry, and it's only getting harder. So lead times coupled with uncertainty on what software will run on it. So I just want to motivate the problem for you, and then I want to talk about what kind of compute structure we're putting in place to anticipate that problem. Okay. So before we get into that, let me talk to you a little bit about what consumers expect from their smartphones. These have changed a lot over time, but now if you think about the list of things that they do here, voice, video, photography, social networking, and so on and so forth. It's actually easy to motivate this. It's much easier in an audience like this. Like, for example, I was coming up on this trip, and all of us have busy schedules and so on. I didn't really get much of a chance to prepare, and so I just was in a meeting in the office, just left from home, caught just drove up to the airport. I didn't have an itinerary, I didn't have a car reservation. I don't know where I'm staying, but it doesn't matter. My admin is working on it, and I have this application that I just downloaded called Tripcase. I don't know if any of you guys use that. It's phenomenal. Every day I come up with a new application that I was thinking, how could I have lived without that? Because I was coming up here, don't have the address, it doesn't matter. It's just everything is in there, and and that's actually now the expectations of people with smartphones, that they've become terrible planners and even worse organizational skills, but they use them. and it frees you to do other things. And actually, sometimes I wonder what we used to do before. I actually have no idea how it used to work. But that keeps changing, and that keeps changing. The other thing that's happened in smartphones is really something I'd like to talk about is the integration of various technologies into smartphones. And what I mean by that is, people used to have their own digital cameras, and you would have, an audio sound system that you use at home, or you'd have an MP3 player, or you'd have a car navigation system, and you'd have a computer to do email and browsers and so on. Now, actually, you just carry one device, and you expect all of them to be in that one device. If you think about that, it doesn't. It's at the surface level, yeah. Well, sure. I'm not saying anything phenomenal, but think about that. So when you have a camera in a smartphone, you expect the camera to perform like how your digital camera performs. I used to tell people, let's say you go to the market and buy a washer and a dryer, and let's say you want a washer-dryer combo. You don't expect it to wash clothes any less than a standalone washer. So that's why when people have a camera in a phone, they don't expect it to perform worse than a digital camera. The expectations and the performance is still the same. But then what's the problem? The problem is it's a small hole. There isn't really much of a lens here, really. And it has to work on a battery, and you only get that much space there. There's no big xenon flashes, big flashes you can throw, but it still needs to take great pictures all the time. And same with the music. When you listen to music in these devices, you don't expect it to sound worse. It should sound like your entertainment system at home. When you put on a pair of headsets, you don't expect a navigation system to give you kind of good directions. It needs to be perfectly accurate, right? So the challenge is facing us is you have to do all these things on this slide and do them as well, at least, as their standalone counterparts in the space that they live in consumer electronics, but still be integrated, and the battery has to last all day. It needs to fit in your pocket. So it's actually a phenomenal challenge if you think about that. And I was telling somebody the other day, if we made as much progress in smartphones, from the time we've started to now in the last few years, if we made that much progress in other things, like if we made that much progress, let's say, cars, they'd be flying, they won't go on the road, right? I mean, that's the kind of progress we've made on these products. And one of the main things is what kind of compute architectures let you do that? What is the compute architecture that allows you to scale to those problems? So if you think of CPU as one of the compute paradigms, you can see that a single core CPU was how we started, and we started working on that quite a bit. Then we went on to multi-core, 2 times cores, 2 times performance, and now you can have quad cores. But what's next? Because I think it's not scalable to just keep putting more processor cores, because I think that really doesn't solve the problem. And I'm going to motivate that a little bit more, by this. Although the industry and the marketing part of this process has been about cores. Like I was, let's say you go to a Verizon store. It's actually a very interesting experience to go to one of these stores. Go to the store that's like a little kiosk in a strip mall. It's actually even better. And you watch people come in, and you watch the guy behind the counter sell a phone. It's actually a great experience. So one time this one person comes in and says, "How about that phone?" "I want that." Well, if it's an iPhone, they don't have to do anything. You can find anything. But if it's not an iPhone and you try to sell this phone, the first thing I was watching this, and whenever I'm kind of bored, I do this. But anyway, so about buy this phone, not that. Why? Well, it's quad core, right? I mean, it's got 4 of them, and that's kind of what are we going to do next, right? I mean, so one of the problems with that concept is that we have to look behind the CPU, and the reason is, if you really think about it, and let me ask you this question: what percentage of the die size do you think of an apps processor is CPU? Greater than 50%? 25, 20. So it's actually less than 15% and getting smaller. So then the question comes, what is the other 85%? What are you guys putting in the rest of the stuff other than some cardboard and paper or something? But actually we put a lot of interesting stuff. And I want to give you a feel for it. So if you think about this, which is somebody asked me a question here just when I was coming up, how technical is your talk going to be? And I keep thinking about that as I present these slides, but I'll try not to make it too technical, but try to make it interesting at the same time. But if you actually take a relative power consumption of doing video decoding, and on the left, on the column there is resolution, and most of the phones, by the way, do 1080p HD now. So the power that it takes to do the video decoding on the CPU versus the power consumption of doing it in a dedicated video engine, it's completely disproportionate and gets worse. The difference becomes much more stark as you go to higher resolutions. So what that means is, in most of these products right now, there is pretty much a dedicated video engine. So whether you have a quad core or a dual core, it really doesn't matter to your video watching. And I just saw a note yesterday, this morning that said by 2015, 60% of all internet content consumed will be for video watching. And most of it is on mobile. So 60% of the watching of the stuff that you do, well, the CPU is not really doing much. Now, don't get me wrong, I mean, my CPU product manager is not here. We make a great CPU. We make a phenomenal CPU, and we made a living out of doing CPUs, and we continue to do that. It's a really important 15%, because it runs a lot of applications, and it's very important to do. But, you know, I'm just trying to balance it by what the CPU does versus what it doesn't. So if I continue to work on that, it's more than the CPU. So what is inside? What is inside these products? So we actually have a CPU. We make a graphics processor engine as a GPU. We actually have a DSP, a custom DSP that we build, and then we put it in there. Actually, the Snapdragon 800 is a full floating point DSP that runs at 600 megahertz, which is kind of ridiculous, which is more performance than most of your Yamaha receivers you have at home. And we put it inside the die in floating point. I used to build those when I was at TI, and now it just takes a small die size in our main processor. The multimedia, which is the video, audio, and so on. What's called ISP, which is actually the camera engine. There's a fairly sizable camera engine there, and how you control these displays, and then the navigation system, the GPS, and so on. So these are all the different blocks that go in. So basically, computing is now about, in mobile phones, is about doing disparate and different execution things, which is what I call heterogeneous, using heterogeneous computing blocks. So the DSP does what it does really well. It does signal processing, floating point tasks really well. The GPU does very interesting things where it goes through a pipeline processing and renders pixels and so on. The CPU does general purpose compute well. The video engine does video decoding and some kind of processing. The display engine has its own kind of flavors of how it does display processing. And the camera engine is a completely different animal. So basically what the market has moved to is these different heterogeneous compute blocks that are specialized to do certain class of applications. And that's what this has become. So mobile heterogeneous computing is really about assigning the right task to the right processing engine. And that's what we spend a lot of time at Qualcomm working on, and that's kind of what I want to talk to you about today. Now, these should all be accessible, and they all need to be programmable. Because anytime you design for something, remember my motivation at the beginning that you really have to call what happens 3 to 4 years from now of people who don't know who are going to write the software. So the only way you can solve the problem is to make them programmable. And you have to not only make them programmable, you have to make them programmable, heterogeneous, tailored towards the applications that they're designed for. And that's how we address this problem. Now, what is not heterogeneous computing? Just putting lots of different CPUs is not heterogeneous computing, although some people like to call it that because the concept of heterogeneous is different. So specialization is key for mobile. So what we've done at Qualcomm is we pretty much have specialized team in every one of these areas. We were just looking the other day. We ship about I think 150, 170 million processors a quarter now. So we ship something that a lot of people don't know. We ship more camera engines than anybody else in the world. We make more cameras than anybody makes. And so just to give you a feel for it, the size of the digital camera market is less than 100 million units a year. We make 6 times that many cameras. So I have more camera processor engineers than actually most camera companies. There's 300-400 people who work on camera at Qualcomm. There's probably 500-600 people who work on graphics. So we have quickly become a camera company, a graphics company, a CPU company, a signal processing company, a navigation company, and so on. And that's the kind of talent that we've kind of accumulated over time now because we had to build expertise in these areas. And what that lets us do is that lets us design processors that are specialized for each of these functions and put them together in interesting ways in one die. So, right task and the right processing engine. So you can see here, I'm talking about 2D to 3D video, image processing and denoising. So, some things work well on a CPU, and some things work well on a GPU. Some things prefer to work on a DSP. But there's also this concept that just because they work on one thing doesn't mean they don't work on the other ones. Like for example, let's say you take a great picture and you want to clean up the noise in the picture. If your camera engine is busy, you could actually use the GPU to clean up the noise. It may not be most efficient because it's not quite designed for that. But we'd like to be able to do that because now we got an engine that you already put the die size in that are living there that you can use that. So what has happened is that we now have to figure out how to get tools and programming environments to be able to perform these tasks on engines that are designed for that, and sometimes not just designed for that, but can do things like that. Now, you don't want to play an MP3 playback on GPU, for example. It doesn't quite work well. But you could do that on a DSP, or you could do it on an ARM or a CPU. So what we do is we build these processors and we make them programmable and we make them accessible. We make tools that actually help you do that. Okay, so the key to doing this is to really have a systems approach. And a lot of people use that terminology. But what I really mean by that is first we need to work on the microarchitecture and the circuit design of building that. And then that comes with the transistor level design. So when we build CPUs, we actually license an instruction set from ARM, and we build our own processor. We build our own caches. We actually design custom transistors to build a CPU. And the reason we do that is because we're able to run them much faster. We did the first gigahertz processor and so on. But we're also able to get the power envelope to be right, because when you design for mobile first, because remember the challenge I told you about having to make these things run an all-day on battery, you have to pretty much design them from scratch. So that's something that we do at the first level, is to have the right microarchitecture, right circuit level design, right transistor level design to get the right building block. The next thing that we do is how do we connect these things together? That's actually a very important problem. And I'll show you that in a minute. For example, when you I'm carrying this Galaxy Note 3. Other good thing about my job is I get to play pretty much with all the phones and I get them free. So it's nice. And on this processor, I was running this application. I don't know how many of you have seen it, but there's an application that they made popular called picture-in-picture. So basically what it does is you pick up the phone and you turn it on, and you get video on the screen, which is nice. But then there's a button you can press and it turns the front camera on too. So now what happens is, you not only see what's going on, you're now on the picture. So this camera and that camera both are firing at the same time. That's kind of interesting because you can kind of put yourself in the picture and see when you took the picture and so on. But then you press a button, it records both, or records each separately. Or you can then take this little block and then of picture-in-picture, and I'll kind of show it to you guys, or if you go by seats, it's in almost all Galaxy cameras. You can take this little window and move it around anywhere on the screen, because sometimes you don't want it to be on the left side because your object may be on the left side. Now what's happening when you do that is that not only you have both the cameras firing, you actually are compositing both the pictures in real time, 30 frames per second. And then you can resize one of them, and it becomes smaller or bigger as you want. Now you're resizing the video and then compositing. Then you can actually change the shape in which it is. Like it can be a diffuse or a circle or an object or a heart shape, so does that. And then you hit the record, it records both of them in video. So when you think about that, the data flow of moving the data from input for each of the sensors, going through the processor, doing the camera processing, hitting the memory, coming out, and at the same time the GPU getting access to the data, the display engine compositing it, and putting it all together, and we are able to hit a button, the video engine comes in and records it in the MPEG, and it gets written to the card real time. So you can just keep recording it till your card gets full. If you get a phone call, you'll pause and you'll still pick up the phone. So that's the complexity of what we do. And that's kind of what I mean by a system level design. Because it's not about making each of those blocks. It's about making each of those blocks and putting them together in a way. And by the way, when you do that, you have to get the power to be within, I think when we did that, we were trying to stay within 900 milliamps or something like that. So you could, even less, maybe 800 or something. So you are able to now record that for, it's a 3200 milliamp hour battery, so you could go for quite some time recording that because you don't want the battery to run out just because you're doing that. So that actually is the second part of it. Now, the third aspect of that is what we can do that, and as I mentioned, we have a lot of smart guys at Qualcomm and smart people, they can do this, but really we don't do that. We need our customers to do that, and we need the app developers to do that, which means we need to provide them all the tools and the software to be able to do that. And that's kind of the third block I talk about, is it's not enough to build the blocks, but actually build the software tools and the infrastructure to be able to build those. So that's the systems approach that we take, and that's what differentiates what we do from what a lot of other people do. And we've done that in the Snapdragon 800, and that's the product that we just launched. And I won't bore you with all of this in the slide. Maybe you guys can get access to the slides if you desire. I think I can get you those. Now that's great in a $900 smartphone, $800 smartphone. Now how do you get this to the masses? How do you get this to everybody who wants to buy a smartphone? What we do then is we build those at the high end, and then I tell people that designing processors, you can think about that as a systems problem in another way, which is you bound the problem by input and output. Now what do I mean by that? If you decide that your phone is going to have a 4K resolution, and your input camera is 13 megapixel, you get one kind of processor. Now if you said my phone resolution goes from 4K to 1080p, to 720p, to wide VGA, you can then scale all your processing elements down to just handle that. And if your input camera goes from 20 megapixel to 8 megapixel to 5 megapixel, you can scale all of them, you can scale the memory. So what we do is we build all these blocks, and we build scalable versions of them. So we have a big GPU and a small GPU, and even smaller GPU, but they all are scalable versions of each other. And the advantage of that is when we make Snapdragon 800, 600, 400, 200, they all look the same, feel the same, operate the same, and the ecosystem that actually works on developing games and applications on one can run on all of them. It just runs on a lesser resolution. And why is that important? That's important because our customers, when they make these processors, they don't want to put a lot of software on just one phone. Once they make one phone, they want to make a whole bunch of them, and they want to reuse the same software. And for an ecosystem like someone who's writing a game or a camera app, they don't want to rewrite this camera app for every different version of Snapdragon. They want to write it on one, and they want it to scalably work on the other. And we're actually a little bit unique in that. Actually, Qualcomm is the only company that makes processors that go all the way from a sub $100 smartphone to a $900 smartphone in a scalable way. Most of our competition actually, comes at one region or the other. So the challenge for us is a little bit more because we need to make them scalable. And a classic example of that is, if you guys see Nokia phones today, you see that there's so many Nokia Lumia phones that have come out. They're all on Snapdragon, and Nokia suddenly started launching them one after the other so fast. And the reason they're able to do that is because they're using the scalable architecture. Okay, so I'm going to switch gears a little bit and actually try to show you some demonstrations of what we are doing and how it feels. So I'll talk about camera, and then I'll talk about a couple other things. So there's and we work a lot with a lot of the startups around here in the valley. I'm here almost every couple of weeks, and a lot of innovation actually comes from not from us, but from the companies here that actually and all over the world that build on top of our process. Here's an example of a company here called Pelican Imaging. Chris and his team have done a nice job of actually taking something called a concept called computational photography. And what I mean by computational photography is the ability to compute instead of just taking a picture. So here what they've done is instead of having one sensor, they have a bunch of sensors and collect the light that comes from all of them and put them together to create a picture that's got depth at every pixel. So now suddenly you have a Microsoft Kinect-like experience with a depth camera. Or you can, the things you can do now is you can take a picture and you can refocus later, like Lightroom did this camera. We're actually able to do that on the Snapdragon. And when we do that, you can see that they're actually operating on all the different aspects of the system. Okay, so I want to show you a couple of things, which is actually the other thing we've done on Galaxy Note 3. This is actually the first phone out there that records in 4K. Actually, it's kind of like probably the best kept secret in the industry, which is kind of sad. I'm trying to get that word out to more people. You can actually take this one and you can put it in the video mode and you start recording. It records at full 4K. It encodes at full 4K. Now 4K is, you're just seeing the 4K TVs coming out. One of the things we thought 3 years ago was that, and of course it plays back 4K content to your TV. One of the things we thought when we did it was that there wouldn't be enough 4K content by that time, but we knew 4K would happen. So we made a conscious decision not only to make a 4K decoder, but a 4K encoder and put it in the phone. So I'm going to motivate this a little bit. There's another company in the Bay Area called GoPro. A lot of you guys may have a GoPro camera. They make a camera which I just saw on their website last week called the Hero or something. It's a $399 camera, fantastic camera. It records 4K at 15 frames per second. You can stretch it to 20 something. It costs $399. When you buy this phone, you get a 4K 30 frames per second that's built into it. It actually is higher performance than your standalone GoPro camera. And takes much less battery power. It's pretty amazing what we put in there, and it comes on that, and we worked on that. And when you do 4K capture, what I've tried to do is I tried to show you a block diagram of all the different blocks in the system, and what block is turned on and what block is turned off when we do that. And that's kind of what they show here. So I gave a part of this talk at a Qualcomm event a month or so ago, where I actually had demonstrations of 4K video and so on. We didn't set it all up today, but it looks stunning when you actually watch 4K on a big 4K screen. And actually what we can do on Snapdragon is not only we can do 4K video capture and playback, some of the newer phones will come with multiple microphones, maybe 4. This already has 2. When you put a couple more, then what you're able to do is, you're not only able to record 4K, you're able to record it in surround sound. So with 4 microphones, we can actually create 5.1 surround. So when you actually play this back, we'll be playing by 5.1 surround with 4K video on your phone. It looks absolutely stunning, and we have a video clip of what it looks like. And soon you'll see a lot more phones doing that. So here I'm going to show you a slightly different demonstration. This actually is again done by another company called GoPanel, IC360. And the concept is this, many times when you record video, one thing that happens is, you take this and you record video and it's great, but then you have to move around and take a record video here and so on. But usually when you're in an environment, let's say at a concert or something, you'd like to record the entire 360 degrees at the same time. So you want to stand in the middle of it and you want to record everything around you. So here, maybe pause it for a second, I'll motivate you for this. What the IC360 guys did is they actually built a little panoramic module that you can actually snap on top of your camera, phone if you like, and you start shooting, and it actually shoots in all directions at the same time. It's pretty wild. Now, you can snap it to a big red camera and whatnot, and now once you have this video, what we're doing here, this is actually a platform that we built. It actually has the same processor that's in my phone, but it's the platform we built last year. It's a reference platform. What we did here is we actually worked with the GoPro, with this IC360 team, and we recorded a scene in 4K in full panoramic. And then what we're doing now is we're actually playing the video in a panoramic way, but you're able to now pull out any piece of it and watch it. So I'll actually play it and you'll see what I mean. So here plays the video, right? And you just watch it, and as the video watches, you'll see. And now what you can do is, what Bala is doing here is just swipe the video across, and you can see that you're actually indexing it to the video. Now, this thing actually rotates. So if you rotate this, you can see it's rotating around. So you can actually rotate into the video, and you can actually play that and rotate it at the same time. I screwed up his demo, but no, I think I just went to someplace. So what that does is, the idea is that you're able to. Now to do this, we not only have to decode the 4K video, we need to pull out the right piece of it, we need to compose it all together and play it back in real time. And we're doing it in real time, 30 frames per second on battery operated device. So this is really phenomenal in terms of, you can see as you rotate around, you can see the camera is actually panning around the scene. This is kind of the experiences that we're talking about that will happen in the future as we build this kind of processing capability into these devices. So yeah, thanks, Bob. So the idea of when you do something like that, if I can get back to my slides, when you do something like that, you can actually see all the different parts of the system that we are turning on when you do that. And really, you can only do this when you have the concept of heterogeneous computing and your concept of using GPUs and CPUs and display engines in the right way to create the right experience. I'll show you another example here. Many times, we build GPUs, and one of the big reasons for GPUs is really to be able to have a great user experience. So something that I see a lot of people do is when you go to a store and buy a phone, the first thing people do is actually this kind of number on it, right? You see that a lot. And actually, first I thought that's kind of silly, like, why, okay, it's smooth or not. Actually, that stresses the processor like nothing else. It really does, because we are actually rendering that UI at 60 frames per second. And the Android UI is a multi-level UI. It's like 4 to 6 layers rendered on top of each other. If you run anything less than 60 frames per second right now, almost everybody in this room can say, that doesn't feel smooth. And that's a lot of it is done by the GPU, and a lot of it is done by the CPU. Now, the same GPU is actually used for quite a bit of gaming. Gaming has become a huge application. Again, just like watching video, we find that the number one monetizable application in any marketplace is actually games. Is by far. Actually, there's really not even a contest. More money is made from downloading games than anything else. When I come here quite a bit to talk to a lot of the game developers, and there's some very interesting statistics I get. I'll give you a little anecdotal one. Like if you look at something like Call of Duty, Modern Warfare, and whatnot. Those things cost like roughly about 250 million to make, those kind of games in that range. And Call of Duty Modern Warfare has a huge payback, and it does pay back quite well. But that actually costs more than most Hollywood movies. I think more than Star Wars, or any of the latest ones. That's the kind of investment that goes into those. But the problem is, that franchise has become one of those franchises where it's about. If you ever wonder why people make Call of Duty 1, Call of Duty 2, Call of Duty 3, Call of Duty 4, because if you didn't make Call of Duty and you call it something else like, Saving Private Ryan, it doesn't work. Because people have got this franchise, and that's the only thing because people don't want to take any risk because the investment is so high. Except in mobile, the amount of investment that goes into games is actually a lot lesser. And the returns are quite high. So for example, a few years ago, people used to invest in games in mobile, and it cost $1 million or $2 million to make, and maybe a few $100,000, and they returned a little bit. But now I heard, like some of my friends tell me that there are a lot of games that make a couple of $100 million revenue, and probably cost $5 to $10 million to make. So the ROI, is much better on mobile games. So what has happened is that we really had to build GPUs that do mobile games well. And what I'm going to do today is I actually want to show you the performance that we've built into these GPUs that deliver. So we worked with a company called GameLoft, which is actually one of probably the most successful mobile games engines, and we actually built this game called Asphalt 8, done by GameLoft. And I'm actually going to play. Bala is going to show you what Asphalt 8 looks like when you run on a tablet and assembled on the screen. And if I didn't tell you it's running on a tablet, you probably think it's some kind of console. So let's play Asphalt 8, and you see what it looks like. Oh, the other thing that we did is when you run Asphalt 8, what we did here is we actually are showing you a few things. The tool that we built, it shows you the loading on each of the 4 CPUs, and it shows you the loading on the GPU. So you can see what clock frequency we are running. So we built this process that actually can be turned off and on. So here the CPUs are actually off, 2 of them. One of them is running 2 gig, the other one is just coming on and off. So but when you play the game, you'll actually see that we'll crank up all the CPUs and all the GPUs, and it pretty much takes all the performance we can offer to build that game. So you can see now the kind of graphics and the quality that we can build on a mobile game. And this game, actually I just downloaded this game. It's 99 cents on my phone. And you try to buy Need for Speed or something like that on Xbox, it's probably a $40, $50 game. So it's completely changing the dynamics of gaming. Now there's a lot of, you have to pay to buy a new car or whatnot, but still sub $5 you can buy so many games. And so the economics are totally different. Because mobile is such a big platform, you can monetize it in volume. So, but then this is the kind of performance and the quality that we expect to get from that. Okay? All right, so I'll try to wrap up here and leave some time for the panel. Get back to my slides. Okay, so that's about high resolution gaming, and actually this game runs beautifully on things like Kindle Fire HD. If you have that Kindle Fire, the one that's coming out, the Kindle Fire HD uses Snapdragon processor and actually has a 2500 by 1600 display. So we are running a game at full frame rate on a 2500 by 1600 display, which, if you think about it, most of the games that you find in consoles are probably running at best 720p, if not 480. We're actually running at full speed on that. And that game that you saw is actually running at 1080p. So we're refreshing every frame at 1080p resolution. And so when you run that game, you can see all the blocks that are lit up when you run the game, and all the blocks that are silent. All right, so those are actually the two things I wanted to show, and the thing I want to show you is actually the what we do in terms of how do we get the ecosystem to use this. So we build these products as soon as our processor comes out, and we actually build the smaller ones, which are like the phone form factor, and then we also build a few other ones like that, which is a bare board, use the same processor. But if you were somebody who's making a camera module, or you're making a display module, you can buy one of those things and connect to that. And if you're a game developer, an app developer, a camera developer, an audio developer, you can use these. And so we provide all these things to all the development community so they can optimize those to Snapdragon almost like a year before the phones come out. So that's why when the phones come out, all the apps run beautifully on that. So now, as I mentioned, it's no longer sufficient to just make platforms. We actually have to make the platforms, and then we have to make a lot of analyzers, profilers, simulators, debuggers, domain tools, and tools at the top of that that lets you program in heterogeneous computing. Because as I mentioned, we give you tools to program the DSP, we give you tools to program the GPU, and so on. And we also spend a lot of time getting industry standard things done on that, so you can actually build on top of that. So that's the so we're pretty bullish on this. We're bullish on heterogeneous computing as a way of computing, and a way of computing for next generation mobile devices. Just because of the disparate nature of the applications and disparate nature of the compute needs. And really, the key to being successful is not only making those processors, but connecting them in the right way, but really providing the tools and the access so that people can build these. And we work on open standards, Chronos and HSA, because open standards that we feel are really, really important, and they build scale, and that's the way we can reach a lot more people. And that's actually all I wanted to share today, and I'll be around a little bit more, and maybe we can take a couple of questions if you guys have, but that's my presentation. Thanks a lot.
Thank you, Raj. We're going to keep this informal. I think we're going to move things around so we get the chairs up here really quick for the panel discussion. As we do that, we're going to talk a little bit. I'm going to ask these guys, some of the professionals who are coming up here in a second, some of the technical professionals, I should say, some questions. But then we want to keep that short. We want to open up the questions for everyone else. So, one of the key things I want to ask you guys is, does anybody want more technical depth? Anybody?
Sure. Yeah.
Good, because you got the guys here. You can geek out as much as you want on these guys, trust me. They're really good at what they do, and they know what they're talking about. So they, let's go ahead and get the chairs up here real quick. We'll try to keep this as informal as possible. Like I said, I want you guys to be able to ask as many questions as you want of these guys. And it can be about the market, it can be about the technology, it can be about, what Qualcomm's doing, or anything else you want. But let's keep the focus mostly on that. We'll try to keep any financials or anything else out of it. So, let me, as Raj indicated, my name is Jim McGregor. I'm the principal analyst and founder of Curious Research. I've got over 25 years in the industry, which I just dated myself, mostly in semiconductors and embedded systems. And I've seen a lot of changes in this industry. I've worked for some of the technology leaders, and for the past 10 years worked with a lot of the technology leaders. So in joining me, we've got three distinguished gentlemen here from Qualcomm. First off, we have Ben Gaster. We have Majid Zaki, and we have Kalin Kaskavar. Sorry, I know I screwed that. I'll let these guys introduce themselves and give a little brief background on each one of them.
Oh, hi, so I'm I'm Ben Gaster from Qualcomm, and I'm working on heterogeneous computing, the design of our kind of next coming devices, and I work from both a hardware and software perspective. And previously and still continue to work on the OpenCL heterogeneous standard and contributing to the next standards.
Imagine.
Yeah, this is Magid Zaki. I'm from corporate marketing. So I'm the less technical here. So don't ask me any technical questions. So basically, my background more was engineering, system engineering, and then I've done some management consulting and working at corporate technical marketing.
And I'm Tulin Cascal. I'm part of the research group. I lead a bunch of projects in the area of parallel and heterogeneous computing. My experience is parallel computing. Before joining the mobile crowd, I was at IBM designing supercomputers like Bluebeam and start my HPCs.
Thank you, gentlemen. I want to start off, we just saw the presentation about, a little bit about heterogeneous computing. Well, first off, you have to understand that the mobile platform, or mobile platforms, especially smartphone tablets, are the innovative platforms for the entire industry. Now, they're what PCs were 10, 15 years ago. Semiconductor processing technology to applications to everything is designed for these solutions. So, Majid, I want to ask you, can you kind of summarize real quickly, what heterogeneous computing is and why it's so important for mobile?
Sure. Yeah. So actually, as Raj mentioned, so I can tell you what heterogeneous computing is and what's not heterogeneous computing. So we think heterogeneous computing is about intelligently using this different kind of processing engines that Raj mentioned in his presentation. And I guess there are two key words. One is intelligently using these processing engines, because you can throw many engines in the SoC, but it depends on how you're going to use them. And then the other key word is fundamentally different kind of processing engines. And that means the CPU, GPU, DSP, the camera processing engine, different kind of engines. So that's why Raj mentioned in the presentation, if you have different kinds of the CPU, we don't consider that as part of the heterogeneous computing. And again, for the smartphone, that's where the innovation is happening, but also, as you know, it's the most constrained environment in terms of thermals and power. And to enable all this high compute power on these devices, you cannot do it with one kind of processor. So if you remember, like from Raj's presentation, he showed this graph of if you run the video decode, actually the CPU versus the video engine, basically you consume 4 more times power on the CPU than the CPU if you run, say, the 1080p case. And take that to any other application. If you run the wrong application on the wrong processor, you are consuming so much power. And then the heterogeneous computing, as we define it, it has, again, running the right task on the right processing engine you have in the SoC, and then the programmability and accessibility, which is very important to us. And I think, as you're going to see at Qualcomm, we are driving that into 2 ways. One is we are evolving each one of these engines to adapt to the new use cases that are happening. And a great example of that is our DSP, for instance, which used to be used only for audio or for voice. And because we own the DSP and we design it in-house, we are able to add more instructions and more functionalities to make the DSP suitable for multimedia applications. So that's something that we are building on. And the other piece is what you're going to hear about a lot is the programming models and tools that we are adding to our heterogeneous computing solutions.
So just to add, right? I mean, it's really about power. I mean, we don't do heterogeneous just for fun, right? And people have been looking at power issues for a long time in the architecture area. And yes, we started building multi-cores, but really the key in mobile and what's driving really heterogeneity in mobile is battery life and thermal characteristics and power dissipation, because you just cannot cool these nice packages very, very tight with, you don't have a fan there. Or unless, you're Intel and then you can put a fan inside there.
I always like, especially being an engineer, when these guys show these block diagrams up there, because they're really simplistic. You don't count the fact that these have maybe 4 or 8 CPU cores, 32 or more GPU cores. I mean, they get really, really intense. So I mean, it's kind of funny to see these simple block diagrams. But when you think about these are essentially what a server was when you start counting the cores and everything else just 10 years ago. I mean, it's phenomenal what we put on these things.
It's a billion transistors.
It really is phenomenal. Now, Ben, we saw that, and he highlighted some of the different compute units that are put on there, from CPUs to GPUs to DSPs to video decode and everything else. But, just putting independent pieces together doesn't necessarily really make it work any better. I mean, you gotta make it better. So, from a hardware and software perspective, can you talk a little bit more about those other critical components, the glue that makes all this work better?
Okay. Yeah, and I think, so actually I'm going to take lead from Callan. I think there are two real aspects from my perspective here. And one, which I'm working on less, but is very important to Qualcomm, is the thermal, and power dynamics. And I think as we expand, the interaction between these different devices, as we start to offload to a DSP or to a GPU or into the camera, things are going to be running at different speeds and different things. And so having thermal feedback at a very fine level is going to be really important. We might today just be running and the thermal sensors kick in and they clock everything down immediately. Now it may just clock the CPU down and they clock the GPU down, but it's very coarse grain and we're not really providing feedback to the system, to the developer. And so I think an interesting area as we go forward is what kind of feedback can we provide from a thermal perspective to an application. And I think one of the games is an obvious one. You may have a huge level of detail that's running on a game, very fine fog effects and those sorts of things, and then you get some further feedback and say in a minute you're going to have to be running a lot less. So rather than just cutting the frame rate down to 20 in the game, becoming a decision. If I had some reasonable amount of time, I could, in my software, make a decision to say, okay, actually, I'm going to drop the fault rates now. I'm going to, lower the to a slightly less detailed texture or stuff like that. So I think that kind of feedback is something that we have to expose in the software models, and the hardware needs to become more integrated in that sense. I think that's an area going. And then the other big thing, I think, Raj said, we have all these devices, we're doing the DSP, the GPU, and the camera, but how do we communicate via these devices? What's the key thing? Well, clearly, we already have a shared memory system. We have a what we call I/O coherency, which means that we don't have to copy data in and out from different devices to other devices. However, the coherency is fairly coarse-grained. I do some changes on the CPU and I affect that memory, and then I tell the DSP to go work on it. And then sometime later I get a message back, and then the CPU can start to process that. So it's a very coarse-grained, and that works pretty well if you just got an image to hand off. But maybe the CPU is not doing anything at that time, or maybe it's more appropriate to take some of that algorithm. So the Pelican one, for example, that we saw that was demonstrated, this has a number of stages, and each of those stages have different kind of compute characteristics that make those different choices for different devices. And we want to make those choices on a fairly fine-grained thing. So we don't necessarily want something to stop running. We want something to communicate back and say, okay, I've done this piece of work, you can work on this now. And so we want to look at the possibility of expanding the coherency domains, making these things more coherent on the finer levels, so it's not just at coarse grain maybe. And I think we're seeing, for example, in the OpenCL standard emerging as there's been a provisional spec produced, and they've talked about shared virtual memory, and they have these different granularities, anything from a coarse grain, which is the one I just talked about really, which we can already do, and is common in the mobile space, to fine grain sharing with actually byte level communication, concurrency. And I think those aspects and how they play out will be really important, will affect the industry as a whole. But the great thing about it is that with the emergence of OpenCL, with C++, and we're seeing a kind of a software standardization on coherency and what that means. But the nice thing about it is that it allows innovation behind those things, and I think Qualcomm is really well placed to participate in that innovation and lead.
It's kind of interesting. You and Colin have both mentioned power, and I've always told a lot of the marketing people in the tech industry that you always have to mention the three P's: performance, price, and power. But it's kind of reversed over the past 5 years. Now it's power, price, and performance. That performance is no longer the key piece. The power is. And that also gets to a key topic that, is really affecting where we're going with the industry. Now we're talking about taking this technology in mobile devices and scaling it down to wearables and to the Internet of Things and scaling it up to the cloud. So, how well does this, or what do we have to do to scale this technology up and down? Calvin?
Well, so that's a very interesting question, and obviously when you go to down to small devices, wearables, and things like this, power becomes even more important, right? And cooling. If you have your watch burning you, it's not going to be very pleasant. So really their specialization. On the other hand, if you look at these wearable devices or smaller devices, they are very, very specialized. So they play very well with designing specialized hardware for specialized applications. Again, you will have to have some sort of heterogeneity there because not everything can be specialized, not all the algorithms can be factored down into these specialized things. So heterogeneity really plays a key role there. If you go and you look at scaling up Internet of Things and really even clouds, I mean, people have been looking at heterogeneous computing there as well to help them with power, with cooling, with total cost of ownership. It's not that much in terms of battery life and how, whether you can keep it powered, but more in terms of cost and cooling and everything else. And that's, again, where heterogeneity is going to play a key role. I mean, we've seen most of the top 500 computers, supercomputers right now have GPUs in them. That's a trend that we are going to see, continuing to see. So heterogeneous compute is going to be everywhere. I'm not sure there's going to be only one model that fits all. Obviously, we have to quite a span of types of applications and things like this. But it's going to be there for all of these.
You're not going to put a Snapdragon 800 in every device?
We certainly want to put a Snapdragon, not necessarily a Snapdragon 800,
Okay.
but a Snapdragon in every device. I think that's our goal. Yes.
But also, I guess that's a great point because I guess we are a system company basically. So what we do is we look at the end-to-end system. When we're doing wireless network, we have been doing that, looking at the network side and the device side. And also when we're doing computing, we are considering that. So on one node or one device, like the smartphone or tablet, we consider what would be the best way to do computing on it and choose the right engine or the right component within the device to do this computing. But also you can scale the idea on the broader side to wearables or servers, for instance. So if you have a wearable device, you may want to do some processing on the wearable device, and you want to do other kind of processing for wearable on the cloud or on the smartphone. And by us having the connectivity and also having the processing power and distributing this processing power properly within each node, that's another form of heterogeneous computing or intelligently doing things in the system.
Right, I want to just expand on that. I think that's one of the advantages of us kind of owning so much different idea blocks is that we have a real opportunity to mix and match these things. We don't have to just say, okay, we can only take from this little pool, or otherwise we have to go over here, vice versa. Now we have this whole pool to take from, and we can, as we develop these different devices and wearables, clearly going to have different requirements to a $900 smartphone, at least in some cases, and so we'll make those trade-offs as they get expanded. I think.
Kind of interesting because that whole distributed computing concept changed servers 15, 20 years ago. So now we're changing everything else.
That's right, and it's going to be software mainly driving these kind of things. I mean, we can build the hardware. That's the easy part.
Well, and let's face it, if we're putting a server on a chip with all these different compute units, you're right, the software is the most critical component and probably the hardest thing to do.
Yep.
So, I mean, we've got different programming models out there with CUDA, OpenCL, and other ones, RenderScript and stuff like that. So, I mean, is there an optimal programming model for these solutions going forward?
Sorry, let me
You
take
wanna take
that. That's a great question, and I frankly will say probably not, because we have so many programming languages, and we see more programming languages arising by today, and some of them are great, and some of them are not so great, will go away, and not for different reasons. And I think that no, I'm not going to predict that. C++ will be with us for a long time, I think. Yeah. But the critical point there is, I think that C++ is a great observation. It started off as a very low level kind of extension to C added object. Some people will say in the embedded community, oh, but it's nowhere near as efficient as C, and I would argue against that. But I think over time they have started to add higher level abstractions, because of the need for it. They've introduced lambdas recently and other things which some people might may have potential performance benefits over writing right to the metal, but that's because they just needed to be able to express new abstractions, and there was enough hardware underneath to execute it. And I think, OpenCL is a very low level, we kind of, can do everything for everyone kind of tool, and it's pretty complicated, and so it's not for everyone, I would argue. And we may argue something similar for CUDA, for example, is quite low level and does things good on their architectures. But I don't think if we made OpenCL really simple and brought it right up to here, it would actually be that useful anymore. We would have lost all the benefits. In the same way that if we took Java and we pushed it all the way down and made it really low level and added everything to it, it would solve everyone's problems, because there's just a different level of sliding scale for different developers and different needs of applications. And I think that OpenCL provides an excellent access to some heterogeneous components today from a native, or Android of course native, whereas Java and RenderScript, for example, provide a great solution for the managed languages kind of program. And I don't necessarily think those two things need to be the same or equal. They may have different benefits to different customers.
So to follow up on that, I think that we are really with heterogeneous compute, we are at the age where we do assembly programming, and I look at OpenCL as the assembly programming for heterogeneous compute, right? And if you continue that analogy, basically, we have a bunch of languages today. C++ is one, but we have scripting languages and Java and managed languages and so on. Not one language is best for every application. In the same way, I see programming models for heterogeneous compute evolving more to suit the needs of the application developers in different areas. Now, fundamentally, there are a number of unique blocks and unique features that everyone has to offer, and things like OpenCL kernels or RenderScript, whatever they call them, or that offload tasks on different devices and asynchronous execution and queues and events and things like this that will permeate all these programming models, but then you can have higher level languages, higher level programming models actually targeting these.
Well, I think Raj highlighted that you almost, even as an SoC company, you're almost a software company because you have to provide that whole suite of tools and everything for everything else. They even introduced recently the Hexagon SDK just for programming one of the four or three? Four, I believe. One of the many DSPs on the Snapdragon that's used for multimedia processing. So, it's really a challenge. So, obviously, heterogeneous computing isn't easy. It's a challenge. But quite honestly, when you start looking at this and looking at heterogeneous computing, this isn't something that is an option. If you want to make a system more efficient, these are things you have to do. So, it's taking companies like Qualcomm to actually be able to improve this solution so that when we look at next generation electronic devices and solutions, they're feasible.
Right, and I actually want to comment on that a little bit. I think that, we can take OpenCL and CUDA with fair examples of this for GPU computing. And, they have introduced a lot of new capabilities that weren't possible. You couldn't get access to that on GPU. Not many people could write that in OpenGL, and you certainly couldn't do some of the more flexible algorithms. And some of those ideas are starting to permutate out of those languages. They're moving into RenderScript, for example, or they've moved into C++ AMP, which is the Microsoft compute language. And I think that over time, we'll see more and more of those ideas start to permutate, and maybe some of them will appear in C++, and some of them will appear in standard Java, and they won't just be languages on the top of those things. And I think that will have a big impact on heterogeneous computing, because you may not even know that you're actually doing heterogeneous computing. If it's just a feature of parallel arrays in Java, who cares whether it's how it gets mapped to the bottom as you as a developer, as long as you are getting performance and power benefits. And I think that that's going to take a while.
Well, we're supposed to have a bunch of entrepreneurs in the room, so what do you guys want to ask these guys?
I have two questions, one directly related, one you really haven't touched on. Can you enlighten us on the partitioning between hardware and software of the camera and the video? Do I have to start over again?
No.
Can you enlighten us on the partitioning of hardware and software on chip for the camera and video encoding, decoding functions? These were traditionally done in hardware, but I'm assuming there's some split. And my second question has to do with the communication interfaces. Your company is noted for, particularly the radio access network interfaces. You haven't talked about that at all. Where does the LTE and 3G and LTE advanced go? I assume that's a separate component or chipset.
You guys have modems?
Maybe.
News for me.
Who wants to start off with that?
Two separate questions.
First off, we'll start off with the camera question.
So I think, the
Camera
camera...
and video encoding.
Yes, so they're pretty separate today. They're pretty separate. They definitely, the camera will work out processing. You'll have some controls for the camera and software that runs on that, and then that will get brought back, into the CPU for do processing and so forth. Any post-processing.
So that's primarily dedicated hardware?
That is dedicated hardware. Now, when I was talking about, the coherency and the kind of shared virtual memory that would expose, you could imagine that over time, that the delineation between the software and hardware will change, and we're looking into that. And I expect, as more and more effects are wanting to be added, some of the things that I was just saying just today with the 360, but we may not want to put all of that in hardware because it may not be wanted for every device, and so there I think there will be a transition to software.
And I think there were two great points that Raj made in the presentation. So again, as you mentioned, how actually this delineation is almost going away. Like some of the camera application that he described, some of the post-processing on the camera use the ISP to do the picture, but some of the post-processing is happening in other engines as well. The other point he mentioned is the different tiers of devices. And even you could think of, there is no one formula to answer, or there is no one answer to that. Because within different tiers, you could choose to do more things on hardware versus more things on software as well.
So I think that's actually a very, fluid boundary that you're talking about. And with this heterogeneous compute and the work that we are doing on programming models and things like this, we are actually trying to blur more of that. Like Maged was saying, if you have a variety of platforms, if you have a developer who's putting together a camera application, they want it to run on as many platforms as possible and get the best out of the hardware. So it's our role as a systems company to give them the tools and the libraries and whatnot to hide that complexity, and we can make better decisions based on knowing the hardware best, how to split it.
I think, sorry, one question. At one point I do
We
want to
haven't
raise.
talked about video at all. Traditionally,
No, I was just going to bring up.
video coding has traditionally been done in hardware, and video decoding in software.
Yeah.
Is that the way you do it, or some other way?
So I'm not sure I can directly say what we're going to speak directly on that done, but we have hardware components for both of those things. And one of the things I was going to raise around that, I think, is particularly around video, is security. No one's mentioned that today, right? And one of the problems with putting it in software or bringing it back to some of these devices which are kind of general purpose and controlled on the general purpose software stack, is that, are they trusted? Do they have, do we need to have new OS abstractions that allow sharing of data between those devices that not everyone, even the OS, can get access to? And I think that is a question that we need to answer, and that may tend to push certain things into hardware and keep it away from the more general purpose compute clusters as we see it.
Yeah.
That's an issue.
Now, your second question was on the wireless interfaces. Qualcomm probably has the most integrated wireless solution on the planet right now. Not only, on the Snapdragon itself, I know that they've got the Wi-Fi, they've got the Bluetooth, they've got the 3G and 4G support, and I know Majid mentioned briefly that that's a critical component to more of a distributed computing architecture. But you want to get more depth on, the impact of those wireless interfaces or the importance of those.
Yeah, so I think, I'm not sure how much depth I can go in that, but yeah, I think, as you mentioned, I guess we have very broad portfolio when it comes to connectivity and cellular connectivity and short-range connectivity as well. So as you may know, we have this integrated, but also think about LTE and LTE carrier aggregation. So I guess we have been offering LTE solution for some time. So we typically say we are on the third generation of LTE, and that translates into two things basically. One is the speeds that you can offer with your LTE connection, but also the experience that we have built over time to come up to this third generation LTE, while competition actually did still trying on the first LTE. And then also we have, in terms of connectivity, we have broad portfolio of connectivity, including the Wi-Fi, the NFC, the navigation. So again, we have been quoted in terms of providing actually as the biggest provider of navigation devices because of the volume we are shipping and in terms of quality as well. So I don't know if that answered your question.
concern that I have, if you have integrated all these communication functions on a chip, including the mixed signal, is twofold. Number one, whenever there's a change in the communications interface, you then have to update the whole chip. And then the second one is if you have any defect in any small part, when you try to fix it, you have to fix the whole chip. This is one of the pitfalls of putting too many functions on an SoC.
So I was going to say, I think that's a reasonable concern, but at the same time, the benefits that we get from integrating it are just outstanding. You know, we reduce power, reduce cost, and you know, it's been a real winner for us. You know, our partners have really seen that as a key offering. So I think that potentially is a downside, but overall, it's not inhibiting for us.
You know, it's kind of interesting because I've been watching this market develop and working with a lot of the different companies in the industry. And several years ago, I looked up and told these guys that, you know, if you look at the integration trends and the technology that's coming down the pike, especially OFDM technology, you know, I said, you know, I think eventually having integrated modems is going to be a differentiator. Now, I had a couple companies look at me and say, no, it's cheaper to have them in a discrete part, and they're basically non-differentiated. There's no differentiation. They're really cheap. Thin modems is the way to go. Those companies that thought that aren't in this segment anymore.
But on the other hand, if you look at the phone platform, it's not likely that you're going to go and replace the modem on the phone anyway.
And there's still a reason to keep some of the analog components on from a manufacturing perspective and power perspective. But, you know, quite honestly, you know, especially when you're looking at combining multiple OFDM technologies like Wi-Fi and LTE, you know, avoiding that wireless coexistence issue, signal coexistence issue that you may have, and being able to multiplex multiple wireless signals and reduce the number of antennas you have in the system, and not only save you on overall system power, but overall system size. So I mean, it really is becoming critical. And you know, just from a market perspective, obviously, you know, low power Bluetooth and Wi-Fi are probably the most critical
I'm
technology.
not sure if I understand what you're saying. You're saying that it is critical to have integrated on the same chip multiple wireless communications technologies, or having multiple wireless communication technologies in conjunction with CPU and GPU and whatever.
There is definitely a differentiated value in having it all integrated in one chip, especially when you're talking about the form factor that if you're trying to fit into the form factor of the palm of your hand or smaller, there's definitely a huge advantage to having it all in one chip. So I mean, it really gets into your trade-off between cost, power, and size.
Thank you very much for the perspective.
Yeah, it's a general question for the panel. Do you see some of the concepts that you guys have developed for your mobile application processor eventually displacing what we would consider traditional compute platforms at home or at work? And are you looking at what you would need to do to then, I guess, augment the current architecture to fulfill that potential mission?
Yeah, I'm not sure how much we can talk about that, but I can imagine that we probably do. But I think it's already happening, right? It's already happening. You know, we're seeing them in TVs, we're seeing them merging into, you know, you can see that integrated into the household more and more. I think one of the interesting things for me, at least, is everyone thought that about tablet. You know, 2 years ago, the iPad came, or everyone was going to PC was gone, laptops were gone, and never quite happened. And I think it's just, for me at least, my perspective is that I really just use my tablet to surf the web and watch videos. It's not really that useful for anything else. That's my personal thing. And so I think some of these other things do have to actually really be good replacements. You know, it wasn't a replacement for a laptop. It was something that complemented the laptop, and it wasn't a replacement for the phone because the phone was in my pocket all the time. So if we're going to replace set-top boxes, or we're going to replace these things in the household and become more integrated, they need to really be a replacement. You know, they need to be better in some way that encompass those previous capabilities. And I think that's still an open question about what that could be.
And the other aspect of it is, I mean, if you look at the Internet of Things or Internet of Everything, right? I mean, you have sensors and we were talking about wearables, but that's another scale down. It's all these sensors that you know, automated homes will have and appliances will have, and there heterogeneous computing, in fact, you know, the ability to compute across this whole range of devices is going to become critical. So some of these technologies that we are talking about here are definitely going towards enabling that kind of.
And I'm not sure I can talk about hardware, the things we're doing in hardware, but I can imagine the things that we are doing in software, the things we are doing, is that we do need, once you have these separate devices in some ways, but they're still seen as a heterogeneous environment, software needs to scale across those in a way that it hasn't done before. In HPC systems, it's really been a struggle to scale from the node to multiple nodes. You've had something like OpenMP or something inside, then you've had the awfulness of MPI, and they're in some ways completely different models, and it just didn't scale, right? And if we want mass applications and kind of Java represented, that they need a way that software is going to scale and integrate that I think we haven't perceived done before.
And I can bet you're not going to run API or DevOps then.
No.
And I would actually give you a different way of thinking about that. Think about all the applications you used to do on a PC that now you do on these other platforms. Think your email, your e-commerce, your video, your your content creation. Think of all these things that once were just relegated to a PC platform that now you naturally do and usually do first on these other platforms. The other thing to consider is if you start looking at some of the, if you just want to really look at raw performance, one benchmark out there that's really good because they have multiple different architectures and multiple different operating systems compared to Geekbench. It's not perfect, but it's one to look at. You look at the x86 architecture advancements over the past three generations. The incremental improvement has been dropping with each generation to where it's now in single digits in most cases. Whereas if you look at the ARM architecture products or ARM-based architecture products, they have increased anywhere from 100% to 350% over the same period. And now we're going to 64-bit, obviously Apple being the first one to introduce a 64-bit ARM-based processor, or ARM-compatible processor. That actually puts these products already in the class of a Core i3 or a Core i5. That's not to say it's going to displace them in any way, because as been said, you still have different usage models for different form factors and different software packages that you may be using on one platform or another. But in many cases, we're already there.
But I do want to take exception a little bit with this focus on performance, right? And in particular on mobile. And why are we working on all this heterogeneous stuff? I mean, again, it's power and thermal. And one thing that's different that we are looking from a software perspective is, it's no longer the HPC kind of thing where you start your API job and you know how many cores you have there and you start your processes and everything like that. On a mobile device, cores will go down just because you reach a thermal limit or, the thing heats up or something, lots of these events. So it's a completely different software model when you think that, the computational resources may or may not be there. It's a much, much more dynamic environment than you had on HPC, where applications, sort of like once you get your allocation, you are set. Now things come and go and move, and depending on the dynamic behavior of the system. The other thing I want to go back to something that Ben mentioned, with the monitoring and feedback related stuff. For programmers, even if you write one application, depending on where you are with your mobile device, you may want to run it in a different environment. You are close to an outlet, you want 1080p out of your video game. You're on a plane where you don't have any power accessible, you may do with less resolution, but want to play the game longer. Same application, different environment. Now, how do you program that thing? That's what we are trying to solve.
Hi, I'm Double. I had a question on like the evolution or revolution, right? So there was PCs, now there's mobile, and due to that you have this heterogeneous computing concept to sort of improve overall situation. How do you see things changing with wearable computing? What are some new type of modules you may need once you have sensors, out of the box of this thing?
I've got my own opinions. But Magic, you want to take that one first?
Sure. Yeah. So So yeah, definitely, I guess, yeah, we see every day like new kind of processing engines emerging. So I guess one thing you mentioned, like we have, say, what we call sensor core or sensor engine. So that's, as you gonna see in mobile, there is this, what we call always on experiences. And I don't know if you saw like this demo, it's called like this Hello Snapdragon, like your phone will be all the time listening to you. And that's through some of the sensors or some of the audio stuff that will be on all the time. And you need specific or specialized engines to run that, because you cannot have the CPU up all the time doing that. So for many of these always-on experiences, you find specialized engines that are coming to do that. And there are so many engines, I guess, that we don't know about today, and we are not even thinking about it, and you're going to see in the future as they develop use cases. So I think it boils back to what Raj was saying in terms of the use cases and how they are evolving and how we think about the future use cases. And then for these future use cases, we have two options basically, either to take the engines that we have and evolve them in a way that will make this use case happen in an efficient way, or come up with new engine like the sensor core or other things to make it happen.
Just to kind of build on that, I think that connected society we're looking at is probably the next major market inflection point we look at. And I think we have to look at it completely differently. We're running into limitations with power, with thermals, with even scaling capabilities with lithography technology and semiconductors. So you almost have to start looking at this as a distributed computing model. So for the first time, you have to think not about what you can cram into a piece of silicon, but where does it belong? Whether it's a distributed platform locally or a distributed platform from the sensor all the way to the cloud. It's a completely different model than we've had before. And we've got, not only do we have a changing technology, but for the first time, because some of this stuff we've been able to do for the last couple of years, but hasn't really taken off. Now we have business models like big data analytics that are going to drive it, because that's going to drive a lot of revenue to companies like Google and Facebook, and they're going to help push this technology. Anybody else? All right, next question.
My question was also quite related. You have these different engines, and as we heard from Raj, the CPU is approximately 15%. Can you give us an idea of how these engines have grown or shrunk over the generations of your processors or your devices, and how do you make that decision when you're planning your next device as to how much real estate you give which engine?
That's actually the core of our business. That's the secret sauce that we are working. I mean, if you look at, maybe I can mention a little bit from an area perspective, right? I mean, we started with single core. Obviously, we started scaling down the process, and so we can fit more of these cores. But we have been increasing them to 4 now, and we'll see how many in the future. Caches have been increasing as well. DSP, we started putting some more of these accelerators. It's really a guessing game that we are doing, depending on the application. No, I mean, like Raj mentioned, right? We have to guess 3-5 years out what is going to be the application. Obviously, in the mobile market, cost is very, very important, and area is directly proportional to cost.
You have a set power budget. You have
Set power
cost budget. You have,
And there's a real battle between the different IP parts, right? Who's going to get the most stuff they want. Everyone wants to be that. If you're in the CPU team, you want your CPU to be the best. If you're in the GPU team, you want that's what that. And so I think in the end, as a company, we have to look at the emerging applications. We have to look at, for example, I think one of the big things that was mentioned on the screen, the screens have gone crazy, right? They've got these huge screens. I mean, Neil showed me his Note 3 and I did one too. I mean, these two things are mad. And so we're pushing a lot of pixels around, and of course at the same time we're seeing things like games, people wanting to do PC, putting PC style graphics on these devices, or at least, at least from a couple of years back. And so one of the places we have seen a lot of growth is in the GPU, and that's certainly a trend that I suspect to continue into some, at least for the short term and medium term. I expect, wherever it's going to come to an end, it's not clear. But at the same time, we've now recently we've announced that we're going to have this programmable DSP that's going to be accessible to general programming. And that's because the DSP is actually pretty tiny and it's pretty small. We can do things, but it's not good at everything. It doesn't push pixels around, but it's really, really good at very specialized operations, image processing in particular, and audio. And there, so it's a real trade-off. That chip doesn't have to be massive yet, but it can actually have a huge impact, even though maybe it's tiny compared to the relative to GPU that doesn't have so much cache.
The other thing is, relating back to the question that we had from there is, this boundary is going to change. And we are going to continue to move things around, push them into hardware, make them, bring them back into software and play with, finding what is really the right boundary. That's why actually we don't want people necessarily to think very, very specifically about, this hardware piece or that hardware piece. We want to offer them the tools to go a little higher and look at the system.
Software, I think that's right. But I just wanted, even though the GPU has grown and the DSP is much smaller, it doesn't mean that one is better than the other. I think that's the important thing to get across. Size is not necessarily the difference. A CPU, a large part of it is taken up by its caches, right?
By the way, if you've ever seen their DSP, GPU, and CPU product managers in the same room, you'd almost swear that they brought baseball bats. It's entertaining sometimes.
Happy family.
It is funny because even when you talk about some of these applications, very much a lot of times they can be run all on one of these cores, or they can be run on multiple cores, depending on how you divide up the project, and that's a huge challenge.
But I think a really important thing to get the ways we have to balance across the system is that there's been a lot of talk about GPU compute over the last few years, particularly desktop computing. With AMD and NVIDIA promoting OpenCL and CUDA or something. But you think about compute seems great. It's going to be great, but I think it's going to go somewhere. But at the same time, we have a trade-offs where the GPU in the mobile space is used all the time, right? Someone's touching the screen, moving it around. You want to do a stupid thing that flicks across just because it gives a 3D view, whatever. And so it is actually used like all of the time. And so offloading compute to it may or may not make sense depending on the application, but it's not such an obvious choice. And so they're trading off. We have a DSP. Maybe it will make more sense to put it onto the DSP because the GPU is already busy 100% of the time, or at least 98% of the time. We can't afford to drop a frame, and so we do something else. So I think there the real trade-offs is that where a device may have made sense in a different domain, HPC or desktop, it may not make sense to use that device for everything in mobile.
And I think that's something that we think is the industry typically focuses so much on talking about the CPU and the speeds and feeds of the CPU. And that's actually, we think, is not the right approach for mobile, definitely, because, again, it's really different from generation to generation, from tier to tier of devices, how much or what kind of compute that you want to mix in the SoC. And this, actually, we have the load analysis team that will spend a long time in these use cases and figure out, to your point, like where things should be run, regardless of the CPU or GPU or DSP product manager. Someone will think, yeah, that makes more sense to run on the DSP or the GPU or the CPU.
So I guess this all really comes down to Raj's crystal ball.
It's
Next question.
So with all these cores on a single die, so they have to obviously share data between them. Traditionally, memory transfer has been the bottleneck. So with all these different cores, are there any new bottlenecks? What are the most challenging things about sharing data between them?
Well, there's some big problems, right? So we have a unified memory, and I suspect that we'll still keep something similar. And so even single bus, and single bus speed, and so But if you think about GPUs, the whole benefit, one of the benefits of GPU is to have a really wide memory bus and to really pound on it, and you high latency by guessing and swapping things in and out. And that's not how it works on the CPU. So there's a real tension here between how to get throughput on the GPU and still maintain access and everything on the CPU, whilst using the same memory. On high-end desktop GPUs, they'll use DDR5 and DDR3 will be on the CPU. We don't have that luxury. We're not going to have, because otherwise we wouldn't have a unified. And so there, the real innovation needs to happen. And of course, we need to be able to run the GPUs at very high speeds of access to the memory while still maintaining cheap memory and allowing the CPU to be able to concurrently access it. At least, even if it may not be concurrently happening, but access it via the same bus. And so that's a real innovation area of space that we're looking at. I think.
And the other aspect on that is, going back to software, we'll have to pay a lot more attention to locality. You cannot keep bouncing things around the chip and expect to get the performance. So you really have to think about more about locality.
And there could be some simple solutions to that. We could add wide I/O memory and that's good. But then we've got a non-uniform memory system, and that in itself introduces its own software complications. Locality might save you there, but it might not. So all of these trade-offs need to be considered, and we're looking at all of that, evaluating it on the market trends and basis together.
But does memory access still look bottleneck, or are there some different constraints to scaling performance?
I think power is actually a bigger concern than even the memory. Again, we build our latest CPU is 2.3 gigahertz. How long do you think we run at 2.3 gigahertz? So
that's definitely true. I think if we could have passed the memory more, and certainly from a GPU perspective, right, we could always do it faster. Memory access, we could run more concurrent tasks. But you're right. At the moment, we're constrained by power. That's still a problem.
So when an application developer writes an application, he's finally going to be using APIs exposed by the operating system, right, the Android or iOS. Then how is he able to take advantage of this? You're saying that an application can run better just because you'll be able to switch into a different core, and like when to use the GPU, when to use the CPU. Are all these exposed to those APIs to the application developer? Or?
So that's actually, we had the answer on, there's your answer. No, the mine one. This is a project that we are working on, in which we actually want to encourage, and it's basically a heterogeneous programming model where application programmers get this notion of tasks. And then, of course, in the beginning, we are working it's more explicit on mapping these tasks. But this is where we want to move people towards. Think about, how you decompose your application and let the system take advantage, know what's underneath, what components are there, and let the system distribute the work across this unit. Now, it's a long way. I'm not saying that, it's going to happen tomorrow. But this is something that we honestly believe that, again, it's that the system becomes both hardware and software. It's not necessary that you're talking directly to the operating system. You no longer, threads are a no-no for me, right? Threads are going to work very well if you have a CPU there. Like I told you, CPUs will go down for different reasons in a mobile device, in a heterogeneous device. So threads are really not the right abstraction for this. Start thinking about tasks, start decomposing your application, and then put it on these devices. Again, developers want something that runs across multiple platforms. There will be a huge diversity. So it's our role to make sure that these applications that are decomposed in such a way run based on what's there, what's the actual hardware. And then, like I mentioned earlier, it really also depends on where you are in what situation. It's very, very dynamic. So even if you have all the hardware there, you might not be able to use it. Like Ben was saying, even if you have a GPU task, you say, I want it to run on the GPU, but the GPU is busy rendering all this other stuff, so you may not have a chance there. That's why we want to decouple that notion from the application program.
Right. So I want to say a couple of things. And I think, RenderScript actually does something similar. Its goal is to abstract away the fact that there's underlying devices, and it will make a decision of where to run it, depending on the load of the system. And also, I think the other key thing today, even on the kind of common denominator of just programming directly to Android, not using any other things, not even rendering, we provide libraries, right? We provide libraries that come on our devices. We give those as part of the driver kits and everything that go to the. And so there, you may not even know, you may just be calling a standard Android library, but we may be uploading it to the DSP for this event. And I think libraries are going to play a huge role of allowing programmers to write to a simple lowest common denominator but still get the benefits of those particular devices, whether it be us or other vendors, competitors.
So how do you see all these things interacting with each other? Because you have MAR there, you have OpenCL, you have RenderScript. I mean, what is exposed to the application there, and how do you see these things? I mean, are they all the same? Kind of doing the same?
Very good question. I mean, fundamentally, they are very, very similar, right? And all of them have this notion of, a compute kernel that you want to offload. They have queues that you schedule them and put them there, and they run on these devices. So there is a set of fundamental abstractions that actually is common across these languages, or these programming models, right? And the way we see it is by, we can have common runtimes that handle all these programming models. And they can be, that's still a debate that's raging, whether you need to push that down into the operating system or you should have a two-level scheduler for these kinds of things. But fundamentally, a lot of the abstractions that they need are common. So we do see that as, much like you have the ISA as the common abstraction for the CPU, we need to raise the level of interface to this common blocks that you execute as tasks or kernels.
I wanted to point out here, these RenderScript really is a Java-based model. It's access from a managed language. Well, the other two on the left-hand side there are native code applications. So it will depend on your application that you're writing. And I think today OpenCL is not supported in Android, but it is actually available on some of our partners who are using it extensively, and we're working with them. And it may not be accessible. So that comes back to that library application. Not everyone necessarily needs to program it, so you can still get advantages of it if you buy the right dice. So so the Motorola X device is an example where that would be happening today.
And in fact, if you look at this, I see this as an inverted pyramid, right? You have very, very few people at the bottom of it, and as you raise, the libraries and things like this, you have more. So libraries programmers is a smaller set than application programmers, than web programmers.
Yeah.
So really, that's the way we see it.
Okay, last question.
So again, from the application developer point of view, they probably want to build for things more than just Qualcomm platforms. There's Apple, Integral, which perhaps hasn't gone into HSA. Do you see any mind share between the different makers where they can agree on something common, something that the application developer doesn't have to tune for every of the 4 platforms there
Well, I just, before these guys chime in on this, I just want to highlight that when you look at some of these different programming models, like OpenCL and HSA, the same companies are represented in the Kronos group and on HSA in a lot of cases. So a lot of cases, these companies are supporting multiple programming models and multiple programming standards for some of the reasons they indicated, because there's different needs. But you guys want to take that a little bit further?
And I think absolutely. So I agree. I think that there is a lot of everyone wants to get one up on everyone else, indeed, so they have their own models. But in the end, I think the standards do emerge, and consensus arises, either because they're forced to do it by just something happens, or it's the right thing to do. I think and I think that's definitely the case in things like OpenCL and RenderScript has been driven by one company, but it's still a standard that is supported by, and I'm pretty sure if you bought any new Android phone, a Nexus phone or whatever, they'd all support RenderScript going forward. And it doesn't matter if we make it or if NVIDIA make it or whatever, that RenderScript is there now, it's part of Nexus, it will be supported. And that's great, because that means developers can target that. Now, it may or may not be the final solution for compute on Android, but it's still a pretty good step forward. And I think, and And well, Murray is something that's coming out of Qualcomm at the moment, so we're going to make it available on all platforms, and so anyone will be able to pick it up. And actually, I use it a lot every day, and I think it's a great model, and I think there will be advantages for everyone to using that model going forwards. It's still an open question of whether it will be successful and will be adopted, but I think Callan's team and Woodham say that one of the key things is that we're opening it up to everyone.
Yeah.
You know, that's a critical thing to make it successful.
On the other hand, I mean, I certainly encourage everybody to use Mari and hope that they will use it. But I think I'm a little more pessimistic than Ben here. I mean, I don't think people will agree on one thing. Not just for technical reasons, maybe economical too. But we touched upon this. Is there one programming model that rules them all? And I don't think that's the case. And then we've seen with Java, write once, run everywhere, it doesn't quite run, So I think that we shall continue to see a bit of diversity in this area.
But I think it's important to understand that Android works. That Google will get into a device, then it will throw over Android for the rest of us, to play with and bring up our devices. And all of us, we work with our ISVs, and then ISVs have their own software stacks. And anywhere in that stack, on top of that, they can add and use these programming languages. So it doesn't need to be very, so if you want to accelerate your Note 3 interface or whatever it might be, which you will want to do if you want to be going like that all the time and burning the CPU cycles, then you can make use of these capabilities even if it's not available on the next phone. But it doesn't matter because it's Samsung's interface that you get on Samsung's phones and they accelerate it. And actually they don't want it to, whatever, I don't know. And so I don't think you should, and then there's the guy who's just writing an app in the App Store who wants it to run on every single phone down to, Android 2.2 or whatever. Then he's not going to use any of this stuff, right? He's just going to use Java-based. So I think yeah, maybe he'll use, I don't know about Android 2.2, anyway. But so there's just going to be different places where I think in the software stack where these things will be. And so there doesn't need to be one winner, one thing. I think there is space for lots of solutions and benefits. And maybe in 10 years' time, Murray will become 90% used by everyone. I suspect that will be the case.
Not on the technical side, the way I kind of simplify this concept for myself, because I'm not that technical, is I think about operating systems. Everyone dreams to have one operating system, and that never happened. And for us, Qualcomm, we have the scale to support major existing operating systems. And I think that applies to programming environment as well. When we see things adapted by the industry, our open standards, we support that on our platform as well.
I'm sure I shouldn't say this, but Linux kernel's probably around 98%. And the rest of the Linux stack, no.
Yeah.
Well, I just
Small
want
one is in it.
There you go. Well, I just want to thank our host Qualcomm for hosting this event and all of you for attending. I hope this was of value to you. And obviously, if you want to talk to any of the gentlemen up here, please go up and swap cards and do whatever you can while you're here. And thank you very much for attending.
Da